Okay, today we are going to learn some things, some things about electric current. About electric current. Electric current is a flow of electric charges, in some direction. In some direction. In this case, we have some average velocity. We have some average velocity of electric charges that we can sign as u plus. We can sign it with u plus. This is average velocity of positive charges. And it is necessary to say that this value is related to both positive and negative charges because motion of negative charges can be described if we have motion of negative charges u minus. It can be described with vector u plus that is directed in opposite direction. Motion of both charges, positive and negative, can be described with one vector of average velocity. It means that I don't need to write this plus in upper index. So I may leave just only average velocity of electric charges. Average velocity of electric charges. And if we multiple this value on if you multiple this value by volume concentration of electric charges, and multiple it by E plus, where E plus is elementary electric charge. I'll remind that E plus is equal 1,602 multiplied by 10 to the power of minus 19 coulombs. This is elementary electric charge, fundamental constant. And this value is some electric charge that comes in the direction of average velocity per unit on time. And this value is known as current density. This is electric current density. Electric current density is a vector that is equal to elementary charge E plus multiplied by volume concentration of these elementary charges and multiplied by average velocity of these elementary charges. So what can we say about this? What can we say more? Maybe you can remember from electrostatics, where we have learned electric flux. And we said that that the integral, for example, integral of for example, vector of velocity of flowing water. If v is vector of velocity of flowing water, and ds, so this is surface integral. So surface integral on some surface S, and this integral is flux, and it will show volume of water that comes through surface S per unit on time, and in the same way we can write this integral. We can write this integral for velocity of electric charges. We can write this integral for velocity of electric charges. So in the same way, if we get this integral, we will have charge. That passes per unit on time through surface S, through some surface S. So we have such formula, and this value dq, first derivative of dq by ds, first derivative, this is value that is known as electric current. E is equal to dq ds. Dt, sorry, dt. T is time. This is time. Okay, and it is necessary to write this in red frame. So I will put this formula together. And from here I can write that this is electric current density. This is electric current density. Electric current density. This value is electric current. This is electric current. This is electric current. This is electric current. Okay, do you have any questions about this? Do you have any questions about this? No questions. It is necessary to say that units for electric current are amperes. And 1 ampere is equal to 1 coulomb divided by 1 second. And sometimes sometimes if you look at some accumulator or battery or uninterruptible power supply, sometimes you can see such a property as in milliampere hours. Milliampere hours. What is this? What is milliampere hour? Let's try to 1 milliampere hour. It is the same as 1 milliampere multiplied by 1 hour, and this is the same as 0.001 amperes multiplied by 3600 seconds, and it will be equal to 3.6 coulombs. 3.6 coulombs. 3.6 coulombs. So this is 1 milliampere hour. So it is a non-systematic unit, no systematic unit for electric charge. Okay, do you have any questions about this? No questions. No questions. That's great. Okay, let's continue. Let's continue. Let's try to understand which conditions are necessary. Which conditions are necessary to supply electric current? To supply electric current. Which conditions are necessary for electric current? If we consider only electrostatic field, we may notice that it cannot support electric current because electrostatic field is potential field. This is potential field, and work of electrostatic field. I will write this with AE. It can be calculated. It can be calculated via integral of electrostatic force and some dr. Electrostatic force, and we know that electrostatic force can be written as electric charge, multiplied by electric field intensity, electrostatic field intensity. This round on integral means that this is integral on closed circle, closed circuit, closed electric circuit, and or some closed line, linear integral on a closed line or along closed line. So this will be E. This will be E multiplied by dr. Multiplied by dr. But electrostatic field is potential field, so it means that this integral is equal to 0. This integral is equal to 0. So only electrostatic field is not enough to support to support electric current. To support electric current in some electric circuit. In some electric circuit. So what to do? To support electric current, we need to apply some force force of non-electrostatic some non-electrostatic force. We need to use non-electrostatic force to support electric current in circuit. Okay, and let's consider the situation when both electrostatic and non-electrostatic forces are present. If electrostatic and non-electrostatic forces are present, we can write that work in this case will be equal to linear integral along closed line, and here in the integral function it will be electrostatic force or force of electrostatic interaction plus non-electrostatic force plus non-electrostatic force dr and here it will be here it can be written this can be written as linear integral closed line along closed line. Here we have charge q multiplied by E, electric field intensity, or not, electrostatic field intensity. It is necessary to notice that I mean just electrostatic field, and plus charge q multiplied by some non-electrostatic field intensity. This value is non-electrostatic field intensity. I'll write this with E, big letter E, with some star above this, and multiplied by dr. And integral function is a linear combination, so it can be written. It can be written in another way. It can be written as q multiplied by linear integral linear integral of E dr plus q multiplied by linear integral non-electrostatic field intensity dr, and this will be equal if we remember that here we have 0, integral of electrostatic field intensity will be equal to 0. Because electrostatic field is a potential field, and because of this here we have 0. Here we have 0 because of this. We have 0. So we will obtain that this will be equal to linear integral on closed line, non-electrostatic field intensity, and multiplied by dr. Okay, do you have any questions about this? Do you have any questions? No questions. No questions. Okay, if there are no questions, let's write this in short way. So work in this case, work along closed circuit will be equal to this. And from here we can obtain a value that is known as electromotive force. This will be E. It is equal to A divided by Q, and this is equal to linear integral on along closed line, non-electrostatic field intensity and dr. And here we have dr. And this value is known as electromotive force of electromotance or EMF. I will write this. So this is electromotive force. Or electromotance or electromotance or EMF So any of this is possible to use. Any of this is possible to use. So it is electromotive force, and I will specially write that E vector E with star is non-electrostatic field intensity. Is non-electrostatic field intensity. So this is non-electrostatic field intensity. Okay, and do you have any questions about this? No questions. No questions. Okay, if there are no questions, I will maybe I will move this here. And let's have a look at some part of electric circuit, that contains electromotance. That contains electromotance. It can be schematically drawn in this way. So here I will here it will be this and this, and so this is a part of electric circuit that contains electromotance. So it will be 1, 2, and here the charge is minus and here is plus. And this is element, this is electromotance or electromotive force. This is electromotance, or this is element of electric circuit that contains electromotive force. E1, 2, for example. It will be E1, 2. Okay. And what do we have in this case? What do we have in this case? In this case, we don't have closed circuit. We don't have closed circuit. We have just an element of electric circuit, so we can write that we don't need this circle near integral, and so in this case okay, in this case we can just write for this part we can just write 1, 2, 1, 2, and 1, 2, and 1, 2. And first integral, you know that that first integral is just potential difference or voltage. First integral is just a potential difference Q multiplied by phi 1 minus phi 2. And the second integral, you know that this is electromotive force. This is electromotive force, so it will be Q multiplied by electromotive force E1, 2. Just for this element, not for all circuit. So for any element of electric circuit, we can write that A, this will be work along this element 1, 2, 1 and 2, 1, 2, and it will be divided by Q, and this can be written as uh, 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 / 2 / 1 can be written as integral of 1, 2, and e plus plus intensity of non-electrostatic field intensity dr, and this will be equal to phi 1 minus phi 2 and plus E1, 2. So it is a result of here. Okay, do you have any questions about this? No questions. No questions. Okay, so we can write that for any element of electric circuit, we can write that it can be written this formula is true for any element of electric circuit. And what is phi 1 minus phi 2? Phi 1 minus phi 2. This is potential difference. U it is equal to U1, 2. And this is potential difference or voltage. Potential difference or voltage. This is potential difference or voltage. And you know that units for voltage are volts, and or unit for potential difference is volt. Okay, and do you have any questions about this? No questions. No questions. Okay, that's great. If there are no questions, we can continue. We can continue. We can continue. We can continue. Okay, and we have learned electric current. We have learned voltage. We have learned electromotive force. And what are connections between them? What are connections between them? Between potential difference and electric current, for example. What are connections between them? And this connection was found from experiment. And it was found by German scientist Georg Ohm in the 18th or 19th century, and it can be written it can be written in this general form. In this general form, it can be written that electric current is equal to phi 1 minus phi 2 plus E 1 2 divided by R, where R is resistance of element of electric circuit, where R is resistance. So we can write that Ohm's law. This is Ohm's law for any element of electric circuit. It can be written in this way. So can be written in this way, and if where R is resistance, R is resistance. It derives from experiment. Resistance is resistance. Where R is resistance, and let's write this in another way. I will just write this as simple Ohm's law. So this is Ohm's law, and if element doesn't contain EMF. If it doesn't contain EMF, so we will have a simpler form of Ohm's law. It will be just E is equal to phi 1 minus phi 2 divided by R, and it will be equal to U, potential difference or voltage, divided by R. Maybe you are familiar with this form of Ohm's law from school, maybe, or maybe not. But we have learned this here. Okay, do you have any questions about this? Do you have any questions? So this is Ohm's law. Okay, and what about resistance? How to define this? We can make a conclusion from experiments that resistance depends on material, and resistance is proportional to long of conductor, and it is in inverse proportion to cross section of conductor. So according to experiment, we can write for resistance 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 it is R is equal to rho multiplied by L and divided by S. Divided by S. Divided by S. Where rho depends on type of material, and in general case it depends also on temperature. So it is rho is electrical resistivity. Electrical resistivity or electrical resistivity or volume resistivity. Volume resistivity. Or volume resistivity. This is the same. Or volume resistivity. For volume resistivity, and L is length of conductor. L is length of conductor. L is length of conductor. And S is area of cross section of conductor. Area of cross section of conductor. So this is resistance. It depends on it depends on size of conductor, and it depends on material. It depends on material. Okay, do you have any questions about this? Do you have any questions? No questions. Okay, let's have a look at some different connections. Some different connections of resistances. First of all, it is necessary to say that resistance on scheme of electric circuit can be drawn with this rectangle. It can be drawn with this rectangle. And let's have a look at connection of resistances in series. Connection of resistances in series. Connection in series can be drawn in this, can be imagined in this way. It can be imagined in this way. So on first on first resistor, we have potential difference for voltage U1. We have electric current I1. Here we have U2, and here we have I2. And first resistance is R1, and the second is R2. And the second is R2. The second is R2. Okay, and how to define voltage, electric current, and resistance of this whole system, of these two elements. How to define? And let's remember. Let's remember the similar situation that we have learned about capacitors. We have learned for capacitors that for connection in series, potential difference may be calculated as sum of potential differences or on some potential differences on these elements. And the same situation is for resistances. So this formula will be true in this case either. This formula will be true for this case. Okay, and okay, and what about electric current? We can remember for capacitor that for capacitors that for connection in series we have the dq is equal to a charge that passes through first resistance, and this is equal to charge that passes through second. Resistance. So what about this? We can divide this by dt, and from here we will obtain that dq by dt is equal to dq1 by dt, and this is equal to dq2 by dt. dq2 by dt. And what is derivative of electric charge? We can remember that this derivative is electric current. This is electric current. So from here we will get that E is equal to electric current through first resistance, and this is equal to electric current through second resistance. Okay, do you have any questions about this? No questions. No questions. Okay, if there are no questions, If there are no questions, I will remove this. I will remove this, and we have already obtained relation between 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 potential difference across these two elements and electric current through these two elements. And what about resistance? We can remember Ohm's law. We can remember Ohm's law, and from this law, we have that electric current may be defined with this equation. So from Ohm's law, we'll get that U potential difference is equal to electric current multiplied by resistance of the whole system, and potential difference across first resistance will be I1 R1, but electric currents are equal, so it will be IR1, I multiplied by R1. And the last that we have, that the same situation for second resistance. The same situation for second resistance, but it is necessary to write lower index 2 instead of 1. It is just necessary, right? Lower index 2 instead of 1. Okay, what questions do you have about this? No questions. No questions. Okay, so we have these three equations. We have these three equations, and we can substitute them here. We can substitute them here, and after substitution, we will get that IR is equal to IR1 plus IR2. And this equation must be true for any value of electric current, and this means that R is equal to R1 plus R2. It will be R1 plus R2. Okay, what questions do you have about this? No questions. Okay, if there are no questions, I will clean some unnecessary things. I'll clean some unnecessary things, and I will leave I will leave only this. Uh, I will leave just this. Okay, so connection of in series. Connection in series. So connection in series. Connection of resistances in series. So in this case, we have such relations for connection in series. For connection in series, we have such situation. Okay, and we can remember, I hope, we can remember that there also connection in parallel, the second main type of connection of elements of electric circuit. Connection in parallel. Okay, what to do in this case? First of all, I will draw a scheme of this for this connection. I will draw a scheme of this connection in parallel, connection in parallel, and in this case, so it can be this, and how to this, and this line, and this, and so connection in parallel. Connection in parallel. So here we have U1, I1, I1, and R1, and U2, I2, and R2. So this is a connection in parallel. Connection in parallel. Connection in parallel. Connection in parallel. And what to do in this case? First of all, we can remember that in this case, the situation will be the same as for capacitor. So potential differences are equal. So U1 is equal to U2, and this is equal to potential difference U. Okay, and what about electric current? What about electric current? From our previous lessons, we can remember that electric charges that passes through the whole system, in case of connection in parallel, will be equal to sum of electric charge that passes through first resistance plus electric charge that passes through second resistance. We have obtained this relation for capacitors, but in this case, it will be the same. It will be the same. Okay, and let's divide this by dt. Let's divide this by differential of time. Dt is equal to d dq1 divided by dq divided by dt plus dq2 and divided by dt divided by dt divided by dt. Okay, and what about these relations? We can remember that this derivative is equal to electric current. It will be electric current. So from here we can derive that electric current through the whole system will be equal to electric current through first resistance plus electric current through second resistance. Okay, what questions do you have? No questions. No questions. Okay, if there are no questions, I'll write this here. So we already have potential difference. We have electric current, and it is necessary to find resistance. And here we will use Ohm's law. Here we will use Ohm's law again. Ohm's law. And for whole system, electric current will be equal to potential difference divided by resistance. For first resistance, it will be equal to U1 divided by R1. And this will be equal U divided by R1. And the same situation will be for the second resistance, I1 and I2. For the second resistance, we have U second divided by R second and this will be U divided by R second. Okay, and after substitution of this formula here, we will obtain that potential difference U divided by R is equal to potential difference divided by R1 plus potential difference divided by R2. And this equation must be true for any potential difference, so it means that it will be 1 divided by R. It is equal to 1 divided by R1 plus 1 divided by R2. Okay. What questions do you have about connection in parallel? No questions. Okay, if there are no questions, let's clean some unnecessary things from the screen. Let's clean some unnecessary things. and just leave what we need. Just leave what we need. So this is for connection. This is for connection in parallel. This is for connection in parallel. This is for connection in parallel. For connection in parallel. Okay, and the next question will be uh, this question will be uh, Ohm's law for any circuit or for circuit that contains of Ohm's law for circuit that contains of resistance and electromotive force. Closed circuit that contains I will type this. So Ohm's law for a closed for electric I will circuit that consists of resistance and EMF. Resistance and EMF. What will we have in this case? What will we have in this case? In this case, first of all, it is necessary to write. So it is necessary to draw this circuit. What I mean is draw this circuit. Here we have resistance. Some connection wires. And here we have EMF. 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 And so such circuit, such electric circuit, okay, and resistance R, and here we have R. R is so-called R is external resistance. R is external or internal. Sorry, is internal resistance, and E is electromotance. So what will we have in this case? What we will have in this case? Let's use our Ohm's law. Let's use this in this case. this case, Ohm's law gives us the next equation. It will be phi1 plus phi2 plus E and divided by R external resistance plus internal resistance. Why plus? Because they are connected, R, big letter R, and R in the little letter R. So external and internal resistances are connected in series, and we know that for connection in series, resistances add to each other. And because of connection in series, we have sum here in denominator. And moreover, this is closed line, and because of this, begin of its line is the same as the end of this line, and it means that phi1 is equal to phi2. So from here we will obtain that this is equal to electromotance divided by R plus R. Okay, what questions do you have about this? No questions. No questions. If there are no questions, let's clean some unnecessary things and just leave this Ohm's law. Let's leave this Ohm's law, and so R is external resistance, resistance is external resistance, and this is internal resistance of electromotive force. Internal resistance of battery or source of electromotive force is internal resistance. This is internal resistance. So this is internal resistance. Okay. What questions do you have about this? Okay. If there are no questions, let's try to have a look. Let's try to understand the properties of electric current in volume. Electric current in volume of conductor. And let's draw some cylinder, infinitely small cylinder inside this volume. Let's draw a cylinder. Let's draw cylinder inside a volume of conductor with electric current. It can be. I will draw this with dash line, because this cylinder is just an image is just a picture. It is not something real. It is not something real. It is just a picture that we need to understand some properties of electric current. Base of this cylinder is ds. Base of this cylinder is ds. Base of the cylinder is ds, and the length of it is dl, because the cylinder is infinitely small. And let's consider a vector. Let's consider a vector dl. Vector dl that has absolute value. That has absolute value that is equal to length or height of this cylinder. So absolute value of vector dl is equal to height of the cylinder. And electric current density inside of this cylinder is J. This is electric current density. And according to this picture, we have that electric current density has the same direction as base of this infinitely small cylinder, and it has the same direction. It has the same direction as vector dl. Vector dl. Okay, and let's use Ohm's law for this situation. Let's use Ohm's law. From Ohm's law, we know that electric current in this infinitely small cylinder will be equal to potential difference and plus E1, 2, and divided by resistance of this cylinder. Okay, and what can we say about electric current? We know that electric current uh, it is necessary to rewrite. I think it is better to rewrite this in another way, that electric current is equal to this integral. It will be the same, but this way is better. Electric current is a surface integral of electric current density. So here we have electric current is equal to electric current density multiplied by ds. And why there is no integral? Because the cylinder is infinitely small. Because the cylinder is infinitely small, we don't have integral here. So we have just J multiplied by ds. Okay, and what about potential difference and electromotive force? From here we can make a conclusion. That this value phi 1 minus phi 2 plus E1, 2 in this case is equal to E electric field intensity plus non-electrostatic field intensity, electrostatic field intensity plus non-electrostatic field intensity multiplied by dl. And again, without integral, because the cylinder is infinitely small. Okay, and resistance of the cylinder can be defined by this formula. Resistance can be defined by this formula. So R is equal to rho multiplied by the length of this cylinder dl divided by area of its cross section. Okay, and from all this formula and from Ohm's law, we'll get that E plus start E and here we have dl. Here we have dl and and here we have rho, dl, and ds. But I think it is better to rewrite it in some another way. It is better to write this with electric current density ds it is better to write this in this way. Okay, here we have made substitution. Okay, and what can we say about this? It can be written in some other way, so plus E electrostatic field intensity plus non-electrostatic field intensity dl and ds divided by rho dl divided by rho dl. Okay, but according to what we noticed above, that the directions of vector j, ds, and dl are the same. Directions of these vectors are the same, and it means that dl multiplied by ds, that this is equal to dl multiplied by ds vector, because this vector has the same direction. These vectors has the same direction. Okay, and so from here we will have that it will be this, and we can remove dl from here, because dl is present in numerator and denominator. So electrostatic field intensity plus non-electrostatic field intensity in brackets multiplied by ds vector and divided by rho. Divided by rho. Okay, do you have any questions about this? No questions. No questions. Okay, if there are no questions, I will rewrite this in short form. I will rewrite this in short form. So from here we have that it can be written. We have this relation, and this relation must be true for any ds. So from here we can obtain that electric current density is equal to 1 divided by resistivity, electrical resistivity multiplied by this, multiplied by electrostatic field intensity plus non-electrostatic field intensity. And it is often written in this way. In this way, E plus E with star above this, above it. Okay, and what is sigma? Sigma is equal to 1 divided by resistivity, and this is electrical conductivity. Electrical conductivity is electrical conductivity is electrical conductivity or electrical conductivity or specific conductance or specific conductance or specific conductance or specific conductance. This is the same. And obtained equation is known as Ohm's law in vector form. This is Ohm's law in vector form. Law in vector form. This is Ohm's law in vector form. Ohm's law in vector form. Okay, do you have any questions about this? No questions. Okay, if there are no questions, thank you for your attention, and I hope to meet you tomorrow. When we will try to solve some exercises. Have a nice day.